So it says, if you have a continuous function, obviously on an interval, and if you know a critical point on that interval, and we definitely know what a critical point is, if we just set up the first derivative to 0 and solve it, then we get our critical points, right? And it could be more than one. So if we know a critical point on that interval where the function is continuous and differentiable, except perhaps at C. So what does it mean? So that means your function is continuous and differentiable everywhere, but it could be not differentiable at C. That means the C could be a corner point, okay? If C is a corner point, your function is still continuous, right? At C, but it's not really differentiable. So even if it's not differentiable at that particular point and continuous everywhere else on the interval, still we can use this first derivative test. Okay, now let's see what is the test, or rather what does the test say? So if the first derivative changes sign from positive to negative as we move to our right, that means as x increases through C, then f has a local maximum. Okay, now what does this mean? Let's see this. Not this one, let's try this one, yeah. Okay, so as you can see, this is our C. The C is critical point here, by the way, okay? And as the statement says, your first derivative changes sign from positive to negative, okay? So here you go. Changes sign, your first derivative is positive here, and this is your critical point, and afterwards you can see your first derivative is negative. So if your first derivative changes sign from positive to negative through C, the statement says we have a local maximum, right? It says that f has a local maximum at C. And you can eyeball it from the graph, right? If it changes from positive to negative, at C, you can see there is a local maximum. Do you agree? So again, we have seen this before. We're just trying to rephrase this using proper mathematical expressions, right? We have already seen this. So can anyone quickly tell me if the first derivative changes its sign from negative to positive through C, what will happen? Anyone?
It means it has a local minimum, yeah?
Exactly. That's it. So if its derivative is calculated on this portion, you will see this goes like this, right? The tangent line, the slope of the tangent line will be negative. That means the first derivative will be negative here. After C, you can see the first derivative is positive, because if you draw a tangent line, you can see it creates an angle less than 90 degrees, right? Any point here on this portion. So it goes from negative to positive after C, right? And you can see we have a minimum point here, local minimum. It may not be the absolute minimum depending on the other part of the function. But if you just consider the interval A to B, I mean AB, I should say, then you can see there is a local minimum here. And that's what the statement says. It says, if the first derivative changes sign from negative to positive as x goes to our right, when we go past C, then f has a local minimum at C. Do you agree? And we have seen another example like this one, So at 6, you can see at 6, it doesn't really change a sign, although 6 is a critical point, right? There is a parallel line here. So that definitely at 6, we have a critical point. But you can see before 6, your first derivative was positive, isn't it? If you draw a tangent line here on this portion, anywhere on this portion, you'll see the slope will be positive, right? It will create a positive angle with the x-axis. And even after the 0.6, you can see it's still positive. It doesn't really change sign after the critical point. Now, what happens when this happens? This is the case. So our statement says, if f prime is positive on both sides near C, or if it's negative on both sides near C, then f has no local minimum or maximum. Or in other words, we can combine minimum and maximum and say extremum, okay? F has no extrema, local extrema, of course, at C. And you can see it, right? You can see it from this graph. It's neither a maximum nor a minimum, is it? It's neither. It's not a maximum, and it doesn't look like a minimum either, right? So if it doesn't change sign, near the critical point, and it could be a possibility, as we can see, then we say there is no extremum. That means there is no extreme values. There is no minimum or maximum values at C. We've seen this, right? Any question from this? No questions at all? Okay, let's move on then. Let's see what we have next. Okay, look at this graph. Isn't it amazing? Right? Okay, I think this is pretty similar to the graph which we have just seen, like this one, right? We've seen this before. This is one more which you can use to clarify your concept, right? So pick up each interval. I shouldn't say interval. Pick up each critical point and check what's happening near those critical points. And how many critical points we have? Let's see. We have 1, 2, 3, 4, 5 critical points. Okay. And at these critical points, we'll see that something is definitely happening. Either we have a maximum, a local maximum, I'd say, or an absolute maximum, or local minimum, or absolute minimum, or it could be neither. It could be no extremum, right? So let's see what informations we can eyeball from each of these graphs, okay? Each of these critical points, I would say. Okay, so if you look at the first critical point, you can see the parallel line here, parallel to the x-axis, of course. So that means definitely we have a critical point here. Uh, so, so if we look at the near points, the neighborhood of this point, we can see it was positive before C1 and it's still positive afterwards. It doesn't really change sign. And in fact, we can easily see that we don't really have any um, mean or max. That means there is no extreme points, extreme values here. And that's what the statement says, right? Let's check the next one. At C2, we can see again there is a parallel line, and before the parallel line we had a positive first derivative, afterwards we have a negative first derivative, and our statement says we should expect a local maximum here. And clearly if you look at the nearby points or the neighborhood, you can see definitely this point is uh, a local maximum point, right? It may not be the absolute maximum because there are higher points, at least one higher point than this, but it's definitely a local max if you consider the nearby points. It's definitely the highest points if you just consider the neighborhood. Do you agree? Okay. And if you keep going on for the other critical points, again, you'll see that's the case. So I think I have already said this, but I should um, tell you again, there is no harm in repeating this rather, that I'll definitely give you a graph like this, okay? And I'll ask you, locate the critical points first, okay? Maybe the first question will say, locate the critical points. That means, where can you see the critical points? The next question could be, from each of those critical points. That means, tell me the behavior at the first critical point or at the second critical point. That means it will ask you to, to, to see if we have a local max there, if we have a local min there, or if it's neither. So you just need to eyeball it from the graph, and that's it. Okay. Let's see what we have next. Okay, 12 times x plus 1 times x minus 1, the quantity squared. If you have a graph like this, we want to see the behavior of the function. Okay. So first of all, quick question. What are the critical points of this? What are, and it's actually half done. Can you locate the critical points from this slide 4.28? Or how many critical points can you see? Anyone? You can actually eyeball it. The critical points are almost there. You can just eyeball it. No one at all? So let us quickly go back to the definition of critical point. If a function is given, how to find the critical points algebraically? What should you do? Forget about this slide. If a function is given, any function is given, how can you find the critical point?
Wouldn't this one just be 1 and -1?
How did you find that?
Because of the, like, it's already factored out for us.
So again, my question is, if a function is given, how to find the critical points from there?
Is it where the derivative is equal to 0?
Okay, I agree. So that means you are trying to say, if I break it down into a couple of parts, the first part is you need to find the first derivative of that function, right? The second part is you need to set that to 0, and then you need to solve it for whatever variable you have. In most cases, you will have x, but you could have other variables like z, t, and all that. So if that's the case, as I said, if you remember, I said the job is half done. You can see it's already the first derivative, isn't it? It's not even the function. They have already calculated the first derivative for us. So the job is half done. Now what's next? What should you do to find the critical points from here? The reason I am trying to break it down into some steps, or I'm trying to explain it, because I'll give you questions like this. I may not give you functions all the time. I may give you the first derivative and say, find the critical point. And I want you to understand what's going on here. Okay? Just don't memorize it that if I'm given a function, I'm going to find the first derivative and then set it to 0 and solve it. No, if the first derivative is already given, now what should you do? Anyone? Can anyone think of anything? What can be done here?
So then you would set those equal to 0.
Set this equal to 0, exactly. As I said, the first derivative is already calculated. So we just set this to 0 and solve it for x. So if we set this to 0, we can see x equals to -1 and +1. So critical points are, as I said, we can eyeball it without any hardcore calculation. Critical points are -1 and 1. Do you agree? Okay. Now, if the graph is not given, can we still find the behavior of f? And the answer is yes. Let's say we want to know what's happening at the critical point -1. So that means we want to know the behavior before the point -1 and after the point -1, right? That means we want to pick some nearby points of -1 on each side, and see how the first derivative is behaving, okay? Like the way we have done it when the graph was given. Now let's say the graph is not given, okay? Just the function is given, and we still want to know what's happening at these critical points. So the most naive approach, although we'll see a better approach soon, hopefully today, but most naive approach would be trying neighborhood, trying the neighborhood of -1, right? So pick up points close to -1 and see what's happening. So if we pick up -2 and plug it in the first derivative, we can see, so since this is a squared term, it will always be positive, no doubts on that. Whatever you pick for x, it will always be at least non-negative. It could be 0, but it will be non-negative. It will never be negative, that's for sure. We know that, right? A squared term can never be negative. But if we pick up any value, excuse me, less than 0 here for this x, it's actually less than, not less than 0, I would say less than -1, we can see this part will be negative. Any value less than -1 here, if you pick any value less than 1 for x, this part will be negative. Do you agree? Let's pick up -2. So -2 plus 1 will give us a -1. You can see the first derivative then becomes negative, right? Same happens for any value less than 1, because this guy will always be positive. So the only change we can eyeball here is with this term. That means we can clearly conclude that before -1, the first derivative is negative, right? Okay. What happens after -1? So if we pick any value greater than -1, same happens with this one. This will always be non-negative, whichever x you pick up. But if it's greater than -1, we can see that this term will be positive. If it's greater than -1, it will always be positive, right? So at -1, we can see it goes from decreasing to increasing, right? It was decreasing initially, and then afterwards it starts increasing. So what's happening at -1? Is it a local min or a local max or neither? Can you identify? Just by.
Is it a minimum?
And why?
Well, I'll just think about like in a parabolic shape. You'd be decreasing on one side, and once you hit a certain point, you go back up on the other.
Exactly, yeah. That's what the first derivative test said, right? And you can actually visualize this in your imagination. Kind of you can set up the picture and try to imagine, right? So that's what the first derivative says. It was negative, and then it became positive after the critical point. This is what's happening here. It was negative, and then it has become positive. So we have a local mean at -1. So you can see we don't really need a graph all the time. Okay, we can actually do it from the function. And again, as I said, we will see a better approach, a much more interesting approach. We are slowly building towards that, okay? All right, and you can actually do this for the other critical point as well. The same reasoning, if you do the same reasoning, you will see that it's actually positive before and after the critical point 1. So we can conclude that for this function, we'll have no extremum at the critical point 1. That means it doesn't really change its sign. So that means it's not really giving us any local mean or maximum value. Okay. All right. Okay, this is the graph of that function. This is the graph of that function. All right. So you can now, the black one, of course, the blackish one, not the pinkish one. The black curve is the graph of the function. And you can see, you can eyeball it and match it with what we just had for the algebraic approach, right? You can see at -1, we have a local mean. Definitely, we have a local mean here, and we can actually say it's the absolute mean, right? Because there is no value less than this, to be honest. So precisely we can say that it's an absolute mean at -1. And at +1, you can see there is no extremum here. It doesn't really give us any mean or maximum value at 1. You can see it from the graph, right? So you can always match it with the graph if you have the graph, or if you know how the graph looks like. But I don't recommend doing that. If you're confident enough, if you know the concept properly, I don't think you should look for the graphs all the time. Initially, you could do that to match it with your concept, but not always, because it will be time consuming. And in most cases, you will not have that much time, okay, to see the graph or to draw the graph and check it. So let's take a break for 30 seconds and see if you have any question, okay? Take your time and try to find rather, if you have any doubts. No questions at all? Okay. Maybe we can practice one. Let's see how much work left for this slide, because we just need to finish this slide today, and we'll be on course with the tentative schedule. So, okay, we have concavity. Okay, that's great. Concavity, inflection point, test for concavity. Okay, cool. So we have lots of things to still lots of things on this slide. That's great. Okay, all right. So let's move on then. We'll try to find a small time in between to practice one or two problems. Okay. Okay, let's see what happens when you have a fraction, because when you're dealing with fractions is often tricky, right? Let's see what we can do. So first of all, I'll ask the same question. Although it can be it can be seen, but my question is, if this expression is given, the first derivative, can you calculate the critical points for me? If yes, how? And I'll not ask what are those, because you can actually see it on the slide. But the question is how to find the critical points from the first derivative like this. I mean, when the first derivative is a fraction. How to find the critical points when you have a fraction? Anyone?
Is that the first derivative that's given to us?
Yeah.
Isn't it? Where is equal to 0? I don't know. Is it where x is 0? I don't know. It's not that, is it?
You're almost there. I wouldn't lie. You're almost there. So if it's a normal polynomial like this one, we know that we just need to set this to 0 and solve it for x. But that's not the only case for a fraction. We have more things to do, right? If you remember. What's that? For a fraction, we have slightly more things to calculate. What's that? You need to remember this because, yeah.
Is it calculating the denominator and numerator separately?
So you're saying that I need to set that,
like equaling them each to 0?
Okay, and why do you think we should set the denominator to 0? Because if you follow the same procedure, like setting this to 0 and solve it, that means if we set this to 0, obviously when a fraction is 0, the numerator is always 0. So that makes sense if we set the numerator to 0 and solve it. But why do we need to set the denominator to 0? What's the reason behind it?
That'll find an undefined point.
Wouldn't it show us holes in the graph?
I wouldn't say holes, because it's the first derivative. It's not the main function. But yeah, I think someone else was trying to say this, that it will help us to find the undefined one. That means where the function is not differentiable. That means if the denominator is 0 at some point, the function is not differentiable at those points. It may be still continuous. We never know. We need to see that it may be still continuous, because if it's continuous, it may not be differentiable. So if the denominator is 0 for the first derivative, that means on those points, or I would say at those points, the function is not differentiable. Or in other words, we could say the first derivative is undefined. And that is another special case we have already seen, right? Like this, like this corner point. The function is continuous. There is no holes, no breaks, but it's not really differentiable at this critical point C, because it's a corner point. So whenever we see a fraction, obviously, like the other polynomials, we need to set this to 0. And if we set this to 0, the numerator will be 0. But we need to set the denominator to 0 separately to see if there is any point where the function is not differentiable or the first derivative is undefined, whichever phrase you want to use. So whenever you have fraction, that's what we do. Obviously, we set this to 0. That means the numerator is 0. But we need to set the denominator to 0 as well. And you don't really memorize it. You just need to understand why is that. Okay. All right. So if we set this to 0, we get these two critical points, 0 from the numerator, or no, sorry, 5/4 from the numerator, because if the numerator is 0, x will be 5/4. And from the denominator, you can see there is a solo x. I mean, the x doesn't have any other terms associated with it. That means plus or minus something else associated with that. So clearly it will be 0 if we solve it for x. So this is the undefined derivative. Okay. All right. So the first job is done, which is finding the critical points. And now we just need to take values nearby, I mean from the neighborhood, and check whether it's decreasing or increasing. So if you take any value less than 0, obviously for this odd exponent, your denominator will be always negative. Do you agree? If you take any value less than 0 for any negative value, the denominator will always be negative because this exponent is odd, right? And if you take any negative value here, it will always be positive because this negative, along with the negative value of x, will make the entire value positive, whichever value you take. Don't trust me, just cross-check by plugging in a couple of values. And if you take a positive value for x, I mean greater than 0, up to 4/5, that means less than 4/5, obviously, you'll see both numerator and denominator will be positive. And it's going from decreasing to increasing again. So once again, we can conclude at 0, we have a local mean. Let's see the graph. Oh, sorry. No. We know that it's from the denominator, right? My bad. Yeah. This critical point 0 has come from the denominator. So definitely at 0, the first derivative will be undefined, right? That means, in other words, there will be a corner point. Although it's decreasing and increasing, since it's undefined, we'll have a case like this, a corner point, right? Do you agree? The black, is this the graph for this one? I hope so. Yeah, it's the graph for this one. Okay, so any question from this type of problems, if the graph is given, if the function is given, although we don't really use this approach, we'll see some better approach on this slide later on, but any question from the graph? No questions at all? Okay, let's move on. So the next theorem says, let's say we have a continuous function and it contains exactly one local extremum. Again, what is extremum? Extremum is the combination of minimum and maximum values. I mean, if we want to rephrase those and combine those together for a single word, we can use extremum. So exactly one local extremum means either we have a local min or a local max, okay? All right, so this theorem says if a local maximum occurs at C, that means if we have a local maximum at a critical point C, then that is the absolute maximum. And if we have a local minimum, then it is the absolute minimum. Now we might be wondering, why is that? Excuse me. Okay, let's see this one. Not this one, I would say, yeah, let's see this one, yeah. So if you take a look at this graph, there is only one local extremum here, right? Only one local minimum here. There is no other local minimum points here. And that's why you can see there is no other points on this graph which is lower, at a lower position than this, in terms of value, which is smaller than this, right? So if we have only one local minimum, you can clearly imagine that should be the absolute minimum for that. Do you agree? Because if you have more than one local minimum, like this one, let's just consider this one without eyeballing anything else. We have two local max, right? One at here and one at here, two local maximums. So if we have more than one local maximum, then we need to compare those and see which one is even bigger. And that would be our absolute maximum. But if we have only one, then that solo local minimum or local maximum has to be the absolute extreme value, right? Do you agree? Just try to understand it. Try to understand what's going on. Why the statement says if we have only one local extreme point, that should be the absolute extreme point. Can you imagine? Take your time, okay? Don't really memorize it. Try to understand why is that.
So that would have, the graph would have to look something like f of x is like x squared.
Okay.
It's like it only has one critical point.
It may have more than one critical point, but it shouldn't have more than one of a kind.
Okay,
that means,
makes sense.
Yeah, if you have a maximum point, that has to be the only maximum point for that. Okay, so let us see. Yeah, like this one. So if you consider this interval, you can see there is only one maximum value, which is here, and there is only one minimum value, which is here. So definitely the local max is here at this point, but it's also the absolute max, right? Because there is no other values which is bigger than this. So that means whenever you have only one local min or max, that has to be the absolute min or max. Do you agree? Does it make sense? Is there anyone who is still confused? Don't look at these red statements. We're not yet there. We're not really talking about the concavity. We are still talking about that particular theorem. I just picked this graph because it looks good. Any question from this? No questions at all? These are obvious things, to be honest, but I don't want you to memorize it. Rather, if you can actually visualize this, if you actually, understand it, the reasoning behind it and all that, that would be even better. That will sustain longer in your brain, right? Okay, let's move to concavity. That's an interesting thing to calculate. And we'll be doing a lot of algebraic approach, a lot of algebraic problem, I should say. We'll be picking up a function, we'll find where it's concave up, where it's concave down, where the inflection points are. We'll be doing lots of problems like this, okay? So let's try to understand what the definition says, and then we'll see, hopefully we'll be able to convince ourselves by eyeballing the graphs, okay? Okay, so the definition says, excuse me, the definition says, if the function is differentiable on an interval, and if it's increasing on I, then the function is concave up on that interval. And if the first derivative is, excuse me, if the first derivative is decreasing, then the function is concave down. Okay, let's see this. Okay, so excuse me, if we pick up this interval from, let's say, -pi to 0, okay, let's say from -pi, not -pi, I should say, okay, let's try the entire interval, -pi to pi, okay? All right, so first of all, if we can imagine this part before the local mean, you can see the derivative is negative, right? And then after the minimum point, the derivative starts getting positive, right? So the first derivative increases, right? And the slopes of the tangent lines increase as x increase. Do you agree? As we are going to our right, try to imagine, try to understand from the graph, okay? As we are going to our right, you can see it's actually increasing. It was negative at first, and then it slowly becomes positive. So the derivative actually increases as we are moving to our right. That means as x increases, the derivative also increases. Do you agree? Do you agree? Don't just trust me. So if that's the case, we say that it's concave up, okay? Let's see what happens here. So as we are moving to our right, as you can see, it was positive initially, and after the maximum point, it starts to become negative. Just look at the slopes. So as we are going to our right, as the x increases, the derivative actually starts decreasing. So if that's the case, we say it's concave down. Okay, that's what the definition says, as you can see. If f prime, that means the first derivative is decreasing, then it's concave down. Okay. All right, now, a really interesting definition, and we'll take a break after we see this definition, and then we'll come back to do some maths. So if the function is continuous, and if it changes, if the function changes its concavity at a certain point, then we say the function has an inflection point at that point. Let's say it's C. So at C, we say the function has an inflection point where, as I said, your function has to change its concavity. That means it was concave down initially, and then it becomes it becomes concave up, or vice versa. That means it goes from either up to down or from down to up. If it changes its concavity at a point, then we say at that point we have an inflection point. Let's see that. Okay, yeah, this one. So you can see, excuse me, you can see this function, whatever it is, the function is not given anyway. This function changes its concavity at C. You might be wondering how. So you can see it was concave down for this part. Okay. And it's concave up for this part. So at this point, the concavity gets changed. Okay. Its concavity gets changed. So we say at C, we have an inflection point. Let's look at this graph to clarify things more. You can see it's concave up everywhere because it was initially negative, and as we are moving to a right, it's getting positive. So it's concave up for this graph. There is no concave down here. It's not really changing its concavity. So what is the algebraic approach for this? So for finding inflection point, we just replicate what we did for critical points and upgrade it to one step higher. That means we just set the second derivative to 0 and solve it. We know if we set the first derivative to 0 and solve it, we get the critical points, right? For the inflection points, we just set the second derivative to 0 and solve it. And this gives us our inflection point algebraically, okay? Graphically, if you can see, in easier words, if you don't see a change of direction here, okay, or here, at a certain point, if you don't see a change of direction like a bowl or something like that, like this one, then you can tell that it's an inflection point. If you can see a bowl-like shape, if you can see it's changing its direction, in other words, if you can see it's changing its direction, right? Then you'll see there is no inflection point at that point because it will not really change its concavity. And if you go to the bookish definition, you can still see this. This is a positive, what should I say? This is a positive first derivative. I mean, the slope of the tangent line here will be positive. And even after this point, your first derivative is positive, right? Can you see that? At this point, it was positive. And even here, it's still positive. But it's changing since definitely we can see it was 0 here, the slope, right? Do you agree? If you draw a slope here, oops, someone is in the waiting room. Okay. You can see the first derivative at this point was 0, right? So whenever you see a shape like this, you can see an inflection point here. okay? All right, let's take a break for, oh, we are almost at 10:10. Okay, let's take a break for 5 minutes and we'll refresh our memories and come back and do more maths, okay? Let's meet at 10:14. And now we'll see the algebraic approach. But before that, if you have any questions, any doubts, we can go over that. Go over those if you have more than one, of course. Any question? No questions at all? Okay, so let's see let's see a couple of more graphs and then we'll see the algebraic approach. We'll just see some special cases now, okay? Like this one. You can see that it says the graph is concave up here and concave down here, okay? So that means at this point, we can clearly see that the function changes its concavity, right? Because the graph says we can trust the graph. Let's say this graph is given, okay? So it's concave up here and concave down here. So that means we can use our definition and say we have an inflection point at this point, C. But even if we have an inflection point somewhere, the second derivative might not exist at that point. Now, what does that mean? We have seen this for critical points as well. That means maybe we have a fraction, or it could be some other cases as well. Let's just imagine that it's a fraction, and the second derivative for that still remains a fraction, and for some values of x, the second derivative becomes becomes undefined. That means, in other words, for some values of x, the denominator of the second derivative gets 0. So that could be a case like this, okay? So that means if you have a fraction for the critical points, we set the denominator of the first derivative to 0 to see where does the first derivative becomes undefined. Same goes for the inflection point as well. We'll be doing this for the inflection point by trying to see where the second derivative becomes undefined, okay? If we have a fraction, if we just set the denominator to 0 and solve it, we'll find those points where the second derivative will not exist, okay? All right. Now, let's see another case. So for this one, we have concave down before this point, we have concave up before this point, and at this point, C, the second derivative does not exist. So if the second derivative does not exist, that's not a problem. The problem is it doesn't really changes its concavity. It's concave down before and after this point. So we say that we don't have an inflection point here. Excuse me. Okay, we don't have an inflection point here. All right, so these are some exceptional cases, okay? And we'll have some problems like this when we'll be doing it algebraically. Hopefully, we'll be doing at least one or two today before we wrap it up, okay? Now let's see whether it means the function has to be increasing all the time if we say it's concave up. And the answer is no. So I wish I could show these two graphs simultaneously. Yeah, kind of. Yeah, can you see both the graphs? Maybe not completely, but at least can you see most part of it? Everyone?
Yeah.
Okay, so you can see this graph, both these graphs are increasing, right? As we are moving to our right, we can see the graphs, both these graphs are increasing. It's on the rise, right? It's definitely increasing as we are moving to our right. As the t value, t gets increased for both the function, you can see it's definitely increasing, but it doesn't mean if the function is increasing, it has to be concave up all the time. You can see for this function, it's concave up, but for this function, even though the function is increasing, it's actually concave down. So a quick remark from this can be derived that an increasing function doesn't mean that it has to be concave up. It could be either. It could be concave up, it could be concave down. We need to see it. We need to see how it's behaving. Okay, if the function is given, we can find it algebraically, no doubts on that. But if the graph is given, we can still eyeball it. And you might be wondering why. So here is a simple example. So as we are moving to our right, you can see the angle, the slope of the tangent, or the angle it's creating with the x-axis is slowly and slowly getting increased. Do you agree? It was kind of flat here and it's getting increased as we are moving to our right. As we are approaching more towards our right, you can see the slope of the tangent is getting increased. Do you agree? You know, the angle creating here looks like this. The angle creating here looks like this. It's definitely bigger as we are moving to our right. And that's what the definition of concave up. Let's see this one. You can see at this point, the slope of the tangent looks like this. At this point, the slope of the tangent looks like this. You know, an angle, it will create an angle like this, right? So as we are moving to our right, the t gets increased. You can see the slope of the tangent is slowly and slowly getting decreased. Can you imagine? If you draw a tangent line here, it will go like this. You know, smallish angle here. But if you draw a tangent line here, it will definitely go like this. A much, much bigger angle. The slope is much bigger here. So you can see, even though the function is increasing, the first derivative is actually decreasing. And our definition says if that's the case, we say it's concave down. Do you agree with this? You don't need to trust me. Just trust your eyes and match it with your concept. Okay, any question from this? No questions at all? Okay, let's see what we have next. This is the most naive algebraic approach again, and we won't be doing it again. We'll be going for a better approach just, I guess, right after this. Yeah, very soon. Yeah, very soon. Okay, so if the first question is, if the second derivative is given for you, can you calculate the inflection point from it? Or what are the things we need to do to find the inflection points from it? Definitely, then you can see the inflection point, but my question is how to do that? When the second derivative is given, how to find, or what should we do to find the inflection points? Anyone?
You have to just do the same thing that you do to find, like what we did before, where you set them equal to 0 and then solve for x.
Exactly, we just need to set the second derivative, which is already given here, fortunately, the second derivative to 0 and solve it. If we solve it for x, we can see x equals 1 and x equals -1/3, right? If we solve this. And using the same approach which we did for the increasing and for finding the increasing and decreasing part of the function, we'll do the same approach for concave up and finding concavity, concave up or down for the second derivative. If we just plug in any value which is less than 1/3, you will see the second derivative will be positive here. If we pick up any value from -1/3 to 1, you will see the second derivative will be negative. Just don't trust me, just plug in 1 or 2 values and check, okay? Let's just try this one. So from -1/3 to 1, we can pick up a value 0, right? 0 definitely lies in between this. So if we take 0 here, let's see what happens. So it's 0 minus 1 and 0 plus 1. So it's -1 times +1. So it's a -1 times 12. You can see the second derivative is negative, right? If you pick any value within this interval, you'll see it's negative. Same goes for this one. If you pick any value which is greater than 1, you'll see this second derivative will be positive, okay? And if the second derivative, the theorem for concavity, the test for concavity, the theorem says, if the second derivative is positive, then it's concave up. If the second derivative is negative, then it's concave down. And if there is a point where the second derivative changes its sign, then we say it's the inflection point, right? So it was concave up since it's positive, it's concave down since it's negative, and it's changing its concavity here, right? So that means it is an inflection point. If we set this to 0 and solve it, it doesn't necessarily give us the inflection point. We have seen this, right? We have seen that we may have a point where we may find a point where it's not there is no inflection. It's not an inflection point. So that's why if we solve it and get values like this, 1/3 and 1, for example, it doesn't mean that there has to be an inflection point there. Rather, we need to check whether it's changing its concavity at that point or not. And the answer is yes. At -1/3, we can see it's changing its concavity. That means it is an inflection point. And same reasoning goes for the second point as well. Any question from this? No questions at all?
Is there any scenario where the second derivative would have a rational function?
Yeah, of course, why not?
What would that look like?
Graphically or what?
Yeah.
So for that, we need to pick up a rational function. I don't think generating one would be ideal. So I would suggest once we are done, if you go to the textbook, you'll definitely see one or two examples. It is not the textbook, by the way. It's the slides for the teaching. I'm not sure whether I have said it or not, but definitely you know this is not the textbook, right? So if you, or for all of you, if you haven't checked the textbook as yet, I hope all of you have. You should. If you haven't, you should check the textbook. You should see the worked out problems, whichever format you have, whether it's the hard copy or the PDF. You should check the worked out problems and practice problems from the exercise, okay? And if you don't find a rational function, I'm pretty sure there will be more than one, but if you somehow don't find any rational functions for which the second derivative is shown, I mean, the concavity and inflection points and all that, just let me know, okay? Let me know, I'll show one on Monday. Because if I try to generate one now, it might not look good because drawing a graph for a fraction is not that straightforward. It often takes time. So I would rather wait for you to find one. If you don't find one, definitely I'll be more than happy to show one on Monday. But let me know beforehand, okay? So that I have the graph before we start. I don't want to waste time on graphing the function. Okay. All right. Now, we have already seen the first derivative test for the extreme points, right? For the minimum and the maximum points. Now, we want to see the second derivative test for it, okay? So for second derivative test, obviously we want to find the second derivative. That means whichever function is given, obviously we'll be doing one or two problems right after we see these statements. So no worries, just bear with me. So whichever function is given, we just need to find this. We just need to find the second derivative, and we want to plug in the critical points there. Okay. And if you remember, to find the critical point, we just need to set the first derivative to 0 and solve it. So it doesn't matter how many critical points are there. We plug in those in the second derivative. And after plugging in second derivative, if the second derivative is positive, we'll say it has a local minimum at that point. Okay. Remember, it's slightly confusing because if it's positive, then it's a local minimum. Okay. And vice versa. That means if it's negative, if the second derivative at that critical point is negative, then we have a local maximum. Okay. And if we plug in the critical point and the second derivative gets 0, then we can't really conclude. We need to do further investigation. We'll see those as well. Okay. So let's see. Let's see if we have examples of this. Yeah. Okay, let's try. Let's see these examples and then we'll practice one or two, okay? So this is a graph where you can see we have a critical point at C, right? And the second derivative at this point is greater than 0. Although since the graph, since the function is not given, we can't really see how the second derivative is 0, greater than 0. But when the function will be given, we'll plug in the value and see that the second derivative is 0 and the function will look like this. Okay, we'll have a local minimum there. So what do I want you to know from these graphs? So I'll give you a graph like this, okay? And I might give you a graph like this and I might ask you for this type of graph at C, what is the second derivative? Your options will be the second derivative is 0, the second derivative is greater than 0, or the second derivative is less than 0. And since you can eyeball a minimum value here, minimum point here, you can straight away say, hey, we have a local minimum here, so that means the second derivative will be positive. Okay, you might see a question like this. And the same goes for this one as well. If you see a graph like this, where you can see a local maximum, that means you can clearly conclude that at this point, the second derivative will be negative. Okay, the function is not given, so you can't really do it algebraically, but you can see it from the graph. Okay, what else? So for a point like this, definitely the first derivative is 0 here, right? Because if we draw a tangent line, it will be parallel to the x-axis. So definitely our first derivative is 0 here. And it is actually changing its concavity here as well. So it's actually an inflection point. So if it's an inflection point, we have seen this graph, right? Just imagine the right half of this graph, not what we have on our left, just from 0 to x, okay? This right half. We have seen this graph before, and we know that it's an inflection point. If it's an inflection point, we know it's the second derivative set to 0 here, right? The second derivative is also 0 here. So you can see if the second derivative is 0, that's an exceptional case. Even we have seen this here. If the second derivative is 0, as I said, we need to investigate further, and we can eyeball it from the graph that it's neither a maximum nor a minimum here, right? So if the second derivative is 0, then we need to see what else we can derive from it. And we can see it from the graph that it's neither maximum nor a minimum here. So that's why we don't have we don't have any extremum here, extreme value here, right? Okay, yeah, now let's do some algebraic problems from it. And for that, I'll share the screen of my iPad, and hopefully it will be more convincing. It will be fun to work with. we'll be finding derivatives. We'll be setting those to 0. And we'll be looking for the concavity. So tons of things we'll be doing. Summer. All right, so it's 0, 6, 18, 21. Let's start with an easier function. Let's say we have f of x. Oops, why do I start with the green all the time? Okay. Let's say our function is x cubed minus 7x squared plus 10x. Okay, let's say this is our function. And let's say the interval is from -2 to 2. And we want to do a lot of things from it. Let's start. First of all, I'll ask you find the critical points for me. So what should you do? The first question could be, find the critical points. What should you do?
First, find the derivative.
First, find the derivative. Very good. Someone else, what's the derivative of x cubed? Just x cubed, not for the entire polynomial. Can anyone tell me?
3x squared.
3x squared, using the power rule, right? Someone else, what's the derivative of 7x squared?
14x.
14x.
14x, very good. And someone else now, what's the derivative of 10x?
Plus 10.
Okay. Now, can someone else answer? Those who have already answered, please let others answer as well. Let others take part in the discussion. So those who haven't answered anything today, can anyone from you tell me what should I do next? I've already found the first derivative. Really quick, can you tell me what should I do next to find the critical point? Or critical points, I would say.
You have to set that equal to 0.
Okay, set this to 0. So we'll have 3x squared minus 14x plus 10 equals to 0. Now we need to solve it. Solve it for x precisely. And we can use the quadratic formula, which is minus b, so it will be positive 14 plus minus. I think we have seen this problem before, right? Yeah, looks like pretty familiar. Anyway, no problem. Let's solve it again. So it will be b squared, so it will be 14 squared minus 4 times ac. A is 3 and c is 10 over 2a, so 2 times 3. Okay, now real quick, can anyone use your calculator and tell me the value in decimal? Just use your calculator and tell me the values in decimals. You don't need to keep it in fractions. At least 2 decimals.
I've got 3.79.
79. Okay, what's the next one?
0.88.
0.88. Thank you. Should we consider both of this? If you see the problem again, should we consider both of these for the critical points? What do you think?
Wouldn't you only use 0.88 because that's in the interval and 3.79 isn't?
Exactly. So we are given a certain interval. That's from -2 to 2, right? So we'll only consider 0.88 because this is beyond that interval. This is outside the interval, right? So for this problem, our critical point will be 0.88. We'll only consider that. So if you're doing it on Pearson, if you plug in 3.79, they will say it's the wrong answer, right? They should, I believe they will. Okay, now the second question would be, find the intervals where your function is increasing. Okay, now what should we do? So if you remember, okay, no, let me ask you, how can we find where the function is increasing? What's the
Isn't that
yeah.
I'm gonna say whether the derivative is greater than 0.
Very good. So we need to find where the derivative is greater than 0. So we know the first derivative, we can copy that from A. It's 3x squared minus 14x plus 10. And we have two intervals from the critical points. Whichever critical point we have, or rather how many critical points we have, we just need to use that to separate the intervals. Since we have one, we'll take only this, 0.88, and the other interval will be 0.88 to 2. So if we had more than one critical points, we would have more intervals using the same procedure, okay? Just have the critical point and start from the endpoints and end at the endpoint. So our critical point is 0.88 and our interval is from -2 to 2. So we'll start from the negative most point or the lowest point, which is -2, and end at the critical point. And then we'll start from that endpoint and go to the other endpoint. We just subdivided the entire domain for this problem into two parts using the critical point. If we had more critical points, we would have more intervals. For example, if we had critical points as 1 and 1.5, just for example, we would have written like this: -2 to 1, 1 to 1.5, and then 1.5, sorry, then to 1.5 to 2. Can you see what I'm doing here? That's how we divide the domain into several parts using the critical point. And now we'll see in which part our first derivative is increasing and which part it's decreasing. So if we pick up any value from this, let's say, I think we can pick up a 0 here, right? We can pick up a 0 from this interval. And we can see if we pick up a 0, our first derivative will be positive. because if we plug in 0, this will be 0, this will be 0. We'll have 10, which is greater than 0. So on this interval, it's definitely positive. So we say our function is increasing in this interval. Oops, sorry, it should be positive 18 here. Right? And if we pick up any value from this, anything from this, up to 2, let's see what's happening. So if we plug in, let's say 1 is 1 false here, right? 1 false in this interval. So this will be 3, this will be negative 14, this will be positive 10. So you can see you'll have a negative 1. So for this part of the interval, our first derivative will be negative. So we'll say our question C will be actually this: find the interval where f is decreasing, and our answer is this, 0.88 to 2. This is the answer for B, and this is the answer for C. So the thing here is to subdivide your intervals using the critical points and just see how it's behaving. Okay, nothing else. But I don't really like this question though, but maybe I'll add 1 or 2 in the homework. What I'm interested in doing is the next parts. The next part is find the inflection point. Okay, I shouldn't say inflection point straight away. Find the interval where it's concave up. Interval 4, I should say here. Find the interval for concave up. Okay, this is what I'll definitely, have in the exam for you. Obviously, the question will say find the critical point, find where it's concave up, find where it's concave down. May or may not have these parts, but it will definitely have the next one, which is find the inflection point. So to finding the inflection point, you actually need to see where it's concave up and where it's concave down. Okay. All right. So for this, for finding where it's concave up, what's the first thing we need to do? Anyone?
Find where the second derivative is positive.
In other words, we want to find the second derivative first, right? So we want to find the second derivative. Now, what's the second derivative? The first derivative was 3x squared. Let me write it for you. Minus 14x plus 10. Oops, sorry. Right? Now we want to find the second derivative. What should we do? We know the first derivative, or even we know the original function. Whichever you think you should use or you can use. What should you do now? What's the second derivative?
Be 6x minus 14.
Okay, so for 3x squared, we can write 6x. For 14x, it's negative 14. So our second derivative is 6x minus 14, right? Okay, to find the interval for concave up, again, we need to set this to 0 and solve it. And then we'll subdivide the intervals like the way we have done here. And then we'll cross-check where it's concave up and concave down. Okay. So if we set this to 0, 6x minus 14 will be 0. 6x will be 14. So x would be 14 over 6. And using your calculator, can you tell me in decimal what it is?
2.33.
2.33. That's pretty fast. Very good. Okay. So again, we have only one. So our interval, oops. It's actually beyond our interval, right? Okay. So that's the problem if we generate one problem. That's why I generally don't create a problem. I actually take one worked out problem so that it doesn't really create any issues. So let's just change this to 2.5, okay? Sorry about that, just for our convenience. Let's just say it's 2.5, okay? And we should change this as well. All of this should be 2.5 because we don't want to waste the time we have spent here, we have invested here. Okay, so now it's definitely lies in the interval, right? Okay, so we can subdivide the interval from -2 to 2.5 into two parts, which is -2 to 2.33, and then 2.33 to 2.5. Can you see what I'm doing here? That's the way to subdivide your intervals, okay? Using the values you get when you set this to 0. And now again, we'll just plug in one value from each and see what's going on, okay? So if we plug in a value here, let's just say we can pick 0 from it. Excuse me. 0 is pretty easy to plug in. So if we plug in 0 here, this becomes 0, we get -14. So our second derivative is negative on this interval, right? And if we plug in any value from this, let's try 2.4. So 6 times 2.4 minus 14. Can anyone calculate it for me real quick? What's the value? I guess it's 0.4, right? If I'm not wrong. I've just calculated at the back of my head, but I was just trying to verify. Is it 0.4?
Yeah.
Okay, very good. So it's 0.4, it's greater than 0. So your second derivative is greater than 0 for this interval. Now, using the definition, we know where is the concave up and where it is concave down. Which interval gives us concave up and where can you find a concave down? Anyone? Just go back to the definition of concavity. I can try to iterate the statement again if you want. So if the second derivative is positive on an interval, then we say our function is concave up on that particular interval, and vice versa for concave down. Now, can you tell me where can you see concave up?
From 2.33 to 2.5.
Exactly. So on this interval here, you can see the second derivative is positive. So our answer for D, I mean, the interval for concave up is this one. This is our answer for D. And again, our answer for our question E would tell you to find the interval where it's concave down. And the answer is already here. The answer for this is this interval, because the second derivative is negative here. Okay, now finally the question F. Find the inflection point, if any. And we have already done all the hard work. We just need to eyeball our previous answers, and that's it. Bazinga, we can say what is our inflection point, if there is any. By just eyeballing this page, whatever you can see it on this page, whatever you can see on this page, can you eyeball and say or conclude, is there any inflection point? If yes, what it is? We have done the calculation. We don't need any other calculation. We just need to use English words to say that this is the reason we say that this particular point is the inflection point. And for your convenience, let me tell you, if at a certain point your function changes its concavity, then we say that's the inflection point. Can you see any point where it's changing its concavity?
Would it be 2.33?
Very good, yeah. You can see before 2.33, it was concave down. After 2.33, it's concave up. So at 2.33, you can see it's definitely changing its concavity, isn't it? Oh, I shouldn't. Okay. Yeah, no problem. Yeah, that should be fine. So you can see at 2.33, it's changing its concavity, isn't it? So that means we have an inflection point. You just need to write it if there is any space why you are choosing it. I mean, if it says, tell us the reason behind it. So you just tell that since at 2.33, at x equals 2.33, of course, our function is changing its concavity, then definitely it's the inflection point. So you can see we have 6 questions from a single problem. And you'll see problems like this in the homework and even, hopefully even in the exam. Any question from this? So all you can see, if you know the definition, it's easy, really easy to calculate this. Yeah, Toriano, yep, go for it.
I just had a question about like our test, or
yeah,
is our next test going to be like the third test and we have a final after that, or our next test is just going to be the final?
Oh, no, you'll have 4 exams. So you'll have the 3rd exam and a really, really smallish 4th exam. There is no real final exam, to be honest, but yeah, you can say that's the final exam, yeah.
Okay.
I'll rather say that the 4th exam, yeah.
Okay.
Mm-hmm.
I also have a question, but it's not about the exam, and I might have just missed it when we were doing it, but on part D, where did you get 2.5 from? Part D.
Oh, okay. So since we generated this problem, when we actually solved the second derivative, we saw it actually gives us 2.33. So we started with -2 to 2, but if that's the case, it actually goes beyond the interval. That's why we changed it to 2.5, nothing else.
Oh, okay. So we just made it bigger because it was
Yeah, we just
Second
wanted to use our concept to find this, nothing else, because whichever problem we'll see, it will have these issues resolved. Okay.
Oh,
Since
okay.
we generated this, we actually had this encountered this problem. Yeah, that's a good
Oh.
question anyway. Yeah.
Okay, thank you so much.
No problem. Okay, any other questions?